Ion product constant for water, Kw. First of all, let's just make a definition. If water is your solvent, then an H plus ion will add to the water. So here's a water molecule, and it will join up with that proton and give you what's called a hydronium ion. So, H plus is the same thing effectively as H3O plus when we're in water. So an aqueous H plus ion is really the same thing as an aqueous H3O plus ion. And you can use them interchangeably. Here's the chemical equation for the autoionization of water. If you have two water molecules, both in the liquid state, they can do proton exchange to give a hydronium ion, H3O plus, and a hydroxide ion, OH minus. The H3O plus is the conjugate acid, and the OH minus is the conjugate base. Now, if we write an equilibrium expression, well, it'll be the concentrations of products over the concentrations of reactants. But we don't include things that are liquids in the equilibrium expression. You don't include liquids or solids. You only include gases or things in the aqueous phase. So it's just going to be the products over 1. So concentration of H3O plus times concentration of OH minus. And the value of that KEQ is 1.00 times 10 to the negative 14th at 25 degrees Celsius. And since this is for the ionization of water, we call it Kw. We could also write 1 molecule of H2O liquid becomes H plus AQ plus OH minus AQ. And so in that case, Kw equals concentration of H plus times concentration of OH minus. It's the same thing, because H plus and OH minus in the aqueous phase are just two ways of saying the same thing. So the value is 1.00 times 10 to the negative 14th. And it's higher at higher temperatures, right? And it's smaller at lower temperatures. The consequence of this is that if we know one, we can find the other. For instance, if we know the concentration of OH minus, then the concentration of H plus equals 1.00 times 10 to the negative 14th over the concentration of OH minus. Here's an exercise. What is the H plus concentration in a 0.050 molar sodium hydroxide solution? Well, we just derived an equation. See above. Pause and work. When you're done, check your answer against mine. So the equation we're going to use is concentration of H plus ion equals Kw 1.00 times 10 to the negative 14th divided by the hydroxide ion concentration. Now, the hydroxide ion concentration, we get that from the solution concentration and the dissolution equation. So if you take sodium hydroxide solid, it's very soluble in water, And when you put it in water, you get a sodium ion and a hydroxide ion. Just one of each. So, the hydroxide ion concentration in sodium hydroxide will be the same as the solution concentration. When is the hydroxide ion concentration not the same as the solution concentration? If it's a weak base, or if it's a base that has a different subscript than 1 on the hydroxide, like calcium hydroxide. But in this case, our solution concentration is 0.05, so that's our hydroxide ion concentration. Which gives us 2.0 times 10 to the negative 13 molar. Now we can find the pH. pH equals a negative log of the hydronium ion concentration. So that's negative log of 2.0 times 10 to the negative 13. Which gives us 12.69. We have 2 sig figs in our concentration, which means we have 2 digits to the right of the decimal in our pH. There's also a shortcut. So our equation for pH is pH equals a negative logarithm of the H plus concentration. Now we know that the H plus concentration equals 10 to the negative 14th over the OH minus concentration. So we can substitute this fraction here. So we have the negative log of 10 to the negative 14th over the hydroxide ion concentration. Now, there's a little bit of algebra here, but you should know that the logarithm of a fraction, say x over y, equals the difference of the logs. So the log of x over y equals the logarithm of x minus the logarithm of y. So our expression for pH that we just derived becomes negative logarithm of 10 to the negative 14th minus the logarithm of the hydroxide ion concentration. So the log of negative 14, or of 10 to the negative 14th, is negative 14. So we have negative 14 minus the negative log of the hydroxide ion concentration, which just becomes 14 plus the log of the hydroxide ion concentration. And this is the pH equation you want to use in basic solution. Back to the situation we had earlier with 0.050 molar sodium hydroxide, we go pH equals 14 plus the logarithm of 0.050. which gives us 12.70. This should be the same answer we got earlier. In fact, it is. I just didn't round correctly last time. Before, I wrote 12.69, but it was really 12.698997, which is 12.70. So this is an effective shortcut.